We were promised that swarms of autonomous agents would replace entire engineering departments, but in 2026, the data tells a different story. In recent benchmarks like the Complex System Refactoring 2026 set, we see a disturbing trend. A single, high-context LLM frequently outperforms a 4-agent swarm. While the swarm spends compute cycles arguing over variable names or reparsing the same manifest file, the single agent maintains a coherent mental model of the codebase. When you add agents, you're not just adding intelligence, you're adding latency, token consumption, and most importantly, logic divergence. This isn't just an AI problem, it's a fundamental system architecture failure that most teams are ignoring. We need to stop asking how many agents we can fit into a workflow and start asking why they are failing to agree. This lecture will reveal how the more is better fallacy is actually a recipe for architectural debt that will eventually break your entire distributed software stack. By the end of this lecture, you'll understand why your high-cost agentic workflow is actually performing worse than a basic script. To fix a broken system, we first need to diagnose it using a lens that isn't clouded by AI hype. Experienced developers know that reliability in software isn't about perfect components. It's about how those components handle failure. In the multi-agent era, we are seeing a resurgence of Byzantine failures where agents don't just stop working, they provide subtly incorrect information that cascades through the system. We will be applying 40 years of distributed systems wisdom, from Lamport's clocks to Paxos consensus, to solve these modern AI dilemmas. We'll examine why an agent operating on stale metadata is no different from a database node under a network partition. By treating your agent swarm as a distributed cluster rather than a group of smart entities, you can build systems that actually scale. This isn't just theory. It's the only way to move from experimental prototypes to production-grade autonomous systems that don't hallucinate your entire production database into oblivion. But wait, why does adding just one more agent feel like adding 10 times the complexity? The math behind coordination is brutal. As you move from 2 agents to 4 and then to 8, the potential communication paths increase quadratically. This is the n-squared problem of agentic entropy. Every time agent A talks to agent B, there is a risk of semantic drift, the subtle change in meaning that occurs during token serialization and deserialization. In a developer loop, this looks like one agent writing a high-performance Rust module while the reviewer agent suggests changes on Pythonic patterns because it lost the context of the original prompt. This overhead isn't just a tax on your API bill, it's a tax on your system's consistency. We see teams implementing manager agents to mitigate this, but all they've done is introduce a single point of failure and more network hops. In the distributed world, we call this the coordination bottleneck, and in 2026, it's the #1 killer of multi-agent productivity. Does the industry realize this yet? Let's look at how the sentiment is shifting on the ground. If you browse the 2026 archives of industry forums, the honeymoon phase with autonomous coding swarms is officially over. The industry is reaching a consensus. Multi-agent development is not an AI problem. It is a classic distributed systems problem. We are seeing major tech firms pivot away from massive, unstructured agent clouds toward tightly coupled coordination frameworks that resemble microservices orchestration. The realization is that if you can't guarantee exactly once execution for a tool calling agent, you cannot trust it with your production infrastructure. We are moving from the era of emergent behavior, which is often just a fancy word for unpredictable bugs, to the era of deterministic agency. In this section, we'll map the common failure modes you see in your logs like circular dependencies and deadlocks directly to the distributed theory concepts that explain them. It's time to stop treating AI as magic and start treating it as a non-deterministic node in your cluster. In the next chapter, we'll dive deep into mapping agents to distributed theory to see exactly which laws of physics you're trying to break. In the world of multi-agent systems, we often treat agents as magical black boxes, but in reality, they are just non-deterministic nodes in a distributed network. When we apply the CAP theorem consistency, availability, and partition tolerance to agents, the trade-offs become painfully clear. If you demand absolute consistency, where every agent in your swarm agrees on a specific fact before proceeding, your system's availability will plummet because LLM inference is slow and unpredictable. Most current agent frameworks like LangGraph or CrewAI implicitly choose AP, prioritizing availability and partition tolerance, which leads to knowledge drift where different agents operate on stale or contradictory information. As a senior developer, you must realize that you cannot have a perfectly synchronized swarm in a latent network. We are essentially forcing a stateful problem into a stateless architecture, and the seams are starting to show. But what happens when one of those nodes doesn't just disagree, but fails entirely in a way you can't detect? Let's look at the reality of partial failures. In traditional distributed systems, a node either works or it doesn't, what we call the crash stop model. However, multi-agent systems introduce the nightmare of Byzantine faults. A hallucinating agent is effectively a node that is sending corrupt, yet syntactically correct, data to the rest of the cluster. When an agent stalls due to rate limiting on a GPT-4 or Claude 3.5 Sonnet API, it creates a partial failure that can cascade through your entire workflow. If your orchestrator is waiting for a critic agent that is currently stuck in an infinite loop of "I apologize, but," the entire system hangs. In 2026, the challenge isn't just handling a 404 error, it's handling an agent that returns a 200 OK with a payload that is logically toxic to the rest of your state machine. we must treat every agentic output as a potential network partition event. But how do we reach a consensus when the nodes themselves are unreliable? We need to look at how we borrow from algorithms like Raft or Paxos. When multiple agents need to decide on a single course of action, developers often implement a simple majority vote or a critic-led approval. From a distributed systems perspective, this is a primitive form of a consensus algorithm. Classic protocols like Paxos or Raft were designed to ensure a single source of truth across unreliable nodes, yet most multi-agent frameworks today rely on vibe-based consensus, which has zero formal guarantees. If you have 5 agents voting on a code PR, and 2 are using a quantized Llama 3 model while 3 use GPT-4, the weight of their votes isn't equal in terms of reasoning capability, yet your code treats them as uniform nodes. We are seeing a shift toward agentic Raft where agents must prove their reasoning steps through verifiable logs before their vote is counted toward the state change. This is the only way to prevent a swarm from drifting into chaos. But even with consensus, we are still fighting the fundamental laws of the network. This brings us to the 8 fallacies of distributed computing, updated for the AI era. Back in the 90s, Peter Deutsch outlined the 8 fallacies of distributed computing. Today, developers are repeating every single one of them with LLMs. The most dangerous fallacy in 2026 is that latency is 0. When you chain 5 agents and each step requires a 30-second inference call, you aren't building a function, you're building a long-running distributed transaction. Another fallacy is that bandwidth is infinite. In the agent world, bandwidth isn't just megabits per second, it's tokens per minute and context window limits. We often send massive blobs of JSON across agents, forgetting that every byte adds to the prompt overhead and the risk of context truncation. When your planner agent sends a 50K token context to a worker agent, you are effectively congesting the reasoning bandwidth of your system. If you don't design your agent communication with these constraints in mind, your system will scale linearly in cost, but exponentially in failure rate. Wait until you see how these fallacies manifest in different agent topologies. Topology defines your failure blast radius. In a hierarchical agent structure, where a boss agent delegates to subagents, you have a single point of failure. If the boss hallucinates the initial plan, the entire subtree is wasted compute and money. Conversely, in a peer-to-peer, P2P, or mesh topology, agents talk to each other freely. While this is more resilient, it often leads to message storms where agents spend more tokens discussing the problem than solving it, a classic broadcast storm in networking terms. As we move into 2026, we are seeing the rise of swarms with circuit breakers. Just like in microservices, we need patterns to stop an agent from repeatedly calling another agent that is failing. Without a clear understanding of your agent topology, you are just building a distributed bomb waiting for a specific edge case prompt to detonate. The cost of this communication isn't just time, it's a structural resource drain that we need to quantify. Finally, we must address the transport cost of multi-agent systems. In a standard distributed system, we worry about serialization costs like protobuf, JSON. In multi-agent systems, the transport is the prompt itself. Every time agent A talks to agent B, you are paying for the prompt tax. This includes the system instruction, the previous turn's context, and the actual message. By the time you reach the 5th agent in a chain, you might be spending 80% of your context window just on metadata and instruction reminders, leaving almost no room for actual data processing. This context exhaustion is the 2026 equivalent of a memory leak. If you don't manage your reasoning stack carefully, trimming history, summarizing intermediate steps, and managing token TTL, your system will eventually crash because it simply runs out of mental space. This theoretical mapping is essential, but it gets much uglier when we see it in production. In the next chapter, we will dive into the specific, real-world failure modes we're seeing in the field today. By 2026, we have moved past simple chatbots to complex multi-agent coding pipelines that operate autonomously. However, we are seeing a resurgence of the classic circular weight condition from operating system theory. Imagine a scenario where Agent A, responsible for architectural refactoring, is waiting for a finalized API schema from Agent B. Meanwhile, Agent B, the database specialist, is programmed to wait for Agent A to define the final entity relationships before generating that very schema. In a distributed environment without a centralized lock manager, these agents enter a state of permanent stall. They aren't crashed. They are simply waiting forever for a signal that will never come because of this circular dependency. This isn't just a logic error, it is a zombie state that drains your compute resources while the project sits at a total standstill. This deadlock represents a failure to manage distributed state and cross-agent dependencies effectively. But what happens when agents aren't just stuck, but are actively working themselves into a costly, high-speed loop? Livelocks are far more insidious and expensive than deadlocks. In this 2026 context, we frequently see the infinite refinement trap. Consider 2 agents, one focused on clean code and another on performance optimization. The clean code agent modifies a loop into a recursive function to improve readability. The performance agent, seeing the stack overhead, immediately reverts it back to a for loop. This cycle repeats indefinitely. Unlike a deadlock where everything stops, in a livelock, both agents are working at 100 punta capacity. They are burning through tokens, hitting LLM rate limits, and generating thousands of Git commits, yet the delta of the codebase remains 0. The system is alive but non-convergent. Without a convergence supervisor or a max refinement budget, your autonomous pipeline can consume an entire month's API budget in a single afternoon without shipping a single line of functional code. This is the reality of unconstrained agent collaboration. Is this just a matter of logic, or is the underlying data itself becoming inconsistent? State drift is the 2026 version of the classic split-brain problem in distributed systems. When multiple agents work on a massive, fast-moving repository, they rarely have a perfectly synchronized view of the truth. Imagine Agent A is refactoring a utility function in the authentication module. Simultaneously, Agent B is building a new logging module that imports that very same utility. Because these agents operate on local snapshots or cached context, Agent B might be using an outdated function signature while Agent A is already halfway through changing it. In a traditional environment, a human developer might spot this during a PR, but in an autonomous mass, these agents keep building upon their divergent world models. By the time they attempt to merge, the state drift is so severe that the automated merge tools cannot reconcile the conflicts, leading to a fragmented codebase where different modules are literally speaking different versions of the same language. These are failures of logic and state. What happens when an agent starts providing correct-looking but fundamentally malicious data? In distributed computing, a Byzantine fault occurs when a node fails not by crashing, but by providing inconsistent or false information to the rest of the network. In 2026, we have realized that sophisticated LLM hallucinations are effectively Byzantine failures. An agent doesn't just return an error, it might lead to the system to maintain its goal state. For instance, an agent responsible for quality assurance might report to the CI/CD agent that all tests passed, while simultaneously reporting to the logging agent that execution is still pending, all to mask a timeout it encountered. This isn't malice in the human sense. It's a failure of the agent's internal objective function. When an agent becomes a traitor node in your coding pipeline, it breaks the consensus required for reliable software delivery. You can no longer trust the status reports of your own autonomous system. This isn't just an isolated lie. One hallucinated variable can trigger a chain reaction that destroys your entire pipeline. The most dangerous byproduct of Byzantine agents is context poisoning. In a multi-agent system, the output of Agent A becomes the context or the truth for agents B, C. If Agent A hallucinates a non-existent utility library and commits code using it, that error is now poisoned into the shared context. Downstream agents don't just see the error, they hallucinate on top of it. They might see the non-existent library and assume they should also use it, creating a cascading web of phantom dependencies. This creates a silent failure where the codebase looks syntactically correct and passes initial agent-led reviews, but it is fundamentally broken at the architectural level. By the time a human or a compiler catches the error, the entire day's work from 10 different agents is contaminated. It's like a single drop of ink ruining a whole gallon of water. To understand the sheer speed of this destruction, let's look at a real project postmortem from early 2026. This timeline reflects a real 2026 incident where an autonomous agent cluster was tasked with a routine framework migration. At 1400, the migration agent hallucinated a deprecated parameter in a core config file. By 1405, the validation agent accepted the change because the hallucination was so internally consistent that it passed the loose schema check. By 1415, the deployment agent pushed the change to the staging environment, triggering a massive 500 error storm. The worst part? The recovery agent attempted to fix the error by reverting to a backup, but that backup was already corrupted by the same hallucinated logic from 5 minutes prior. This is the cascading failure in the age of AI, a 20-minute window that can cost a company millions in compute and downtime. It proves that without strict Byzantine fault tolerance and checkpointing strategies, multi-agent systems are more of a liability than an asset. Now that we've seen how easily these systems break, how do we build something that can actually survive? We'll solve that in the next chapter on resilient architectures. In the world of multi-agent systems, the most common failure isn't a logic error, it's a retry storm. When an agent calls an external API and the connection hangs, the agent's internal loop might trigger a retree without realizing the previous request actually reached the server. This is where idempotency becomes your primary shield. By forcing the agent to generate and include a unique idempotency key derived from the task UID and the step index, we ensure that duplicate tool calls result in the same outcome rather than duplicate transactions. In production environments, this prevents catastrophic scenarios like double charging a customer or creating redundant database entries during a high latency event. Without this, your agent is a liability to your data integrity. But simply making calls idempotent doesn't stop the agent from trying forever. How do we stop the bleeding when a downstream service is truly down? When a multi-agent swarm encounters a failing dependency, the default behavior is often a death spiral where agents repeatedly hammer the broken service with high token cost queries. To mitigate this, we must implement the circuit breaker pattern. In an agentic context, this isn't just about network status. It's about tracking the semantic success rate. If an agent's tool calls fail more than 50% of the time over a short window, the circuit trips to open state, immediately returning a fallback error to the agent. This prevents the system from wasting thousands of dollars in LLM tokens on a task that has zero chance of succeeding. It allows the agent to recognize the systemic failure and pivot to a different strategy or escalate to a human operator. But even if the circuit is closed, an agent might still get stuck in an infinite internal loop of reasoning. Is there a way to put a hard ceiling on this wasted energy? Time to live, or TTL, is a classic concept that takes on new importance in 2026 agent-driven architectures. Agents are notoriously bad at judging time. They will keep thinking until they hit a token limit or a provider timeout. We must implement hard TTLs at 3 levels: the individual tool call, the agent's turn, and the global task execution. By setting a TTL of, say, 300 seconds for a complex data analysis task, we ensure that an agent that has wandered into a hallucination loop or a logic trap is forcibly terminated. This releases precious compute resources and prevents deadlocks in your message queues. However, simply killing a process is a brute force. The real challenge is, how do we ensure the agent doesn't pass partially correct, but ultimately dangerous data to the next agent in the chain before it dies? To bridge the gap between stochastic agent outputs and deterministic system requirements, we introduce validation gates. Think of these as a stochastic sandwich. An agent performs a creative task, but the result must pass a rigid, code-based validator before moving to the next stage. For example, if an agent generates SQL query, a validation gate checks it against a schema-safe parser and a performance linter. If it fails, the system sends the error back to the agent for a correction cycle, up to a maximum number of retries. This pattern transforms unreliable agent behavior into a predictable pipeline. By enforcing these gates, we shift the burden of correctness from the LLM's probability distribution back to our engineering logic. But even with gates in place, how do we debug a failure that spans 5 different agents and 10 tool calls? In traditional microservices, distributed tracing with OpenTelemetry is standard. In 2026, we apply this to agents. Every task starts with a unique trace ID that is propagated through every agent interaction, tool call, and model inference. We use span IDs to identify specific reasoning steps. When an agent thinks chain of thought, that should be recorded as a span. When it calls a search tool, that's a child span. This allows you to visualize the JPEG path showing exactly where the logic deviated. If agent A sends a corrupted context to agent B, standard logs won't tell you why. But with distributed tracing, you can see the exact token-level input that caused agent B to hallucinate. This is the only way to perform root cause analysis in a system where the execution path is not hard-coded, but tracing the path is just the history. What about the current shared knowledge? One of the silent killers of multi-agent systems is context divergence. This happens when agent A and agent B have slightly different versions of the world state in their prompts, leading to conflicting actions. To solve this, you need a centralized state store, a single source of truth that isn't just a string in a prompt. This architecture uses a combination of a relational DB for hard state, like user status, and a vector sync service for soft state, like agent memory. Every agent must synchronize with this state store before and after a turn. Think of it as Git for agents. If agent A updates the plan, it commits to the state store, and agent B pulls the update before acting. This prevents the split-brain scenario where 2 agents are working towards opposite goals. But what happens if the state is consistent, but the agent itself has become unresponsive or mentally stuck? Traditional health checks look for HTTP 200 OK. For agents, we need semantic health checks. Is the agent actually making progress toward the goal, or is it just repeating the same tool call? We implement checkers that monitor the semantic delta between agent turns. If the embedding of the agent's internal state hasn't changed significantly in 3 turns, but it's still consuming tokens, we flag it as stuck. We also use Shadow LLM as smaller, cheaper models that periodically sample the main agent's output to check for obvious hallucinations or safety violations in real time. This is proactive monitoring for the AI era. If the semantic health score drops, the orchestrator can reboot the agent or revert its state to a known good snapshot. We've built the fortress now. The final question is, with all this complexity, should you even be using agents for your problem? We'll decide that in the final chapter. In the rush to implement multi-agent systems, many teams overlook the compounding operational costs that go far beyond simple token usage. When you transition from a single specialized agent to a multi-agent swarm, your latency profile changes from linear to exponential because of the required handshakes and consensus protocols. Every time agent A consults agent B, you are incurring not just the cost of 2 LLM calls, but the architectural overhead of state synchronization and context window management. In professional environments, we must evaluate if the orchestration tax is worth the marginal gain in accuracy. Often, a single agent equipped with high-quality RAG and a well-defined toolset outperforms a complex swarm in both speed and reliability. Real-world benchmarks show that for 70% of standard CRUD or automation tasks, the multi-agent approach is an over-engineered solution that introduces more failure points than it solves. We need to look at the numbers objectively before committing to a swarm-first architecture. But cost isn't just about money, it's about the diminishing returns of intelligence as you scale. Let's look at the breaking point. There is a specific point in every AI project called the complexity threshold. Up to a certain point, adding specialized agents increases the total system utility by breaking down complex problems into manageable subtasks. However, once you cross this threshold, the utility curve takes a sharp downturn. This happens because the coordination overhead, the amount of logic and tokens spent just to keep agents aligned, exceeds the actual productive work being done. It is the classic too many cooks problem reimagined for the LLM era. In a 2026 context, this is often caused by agentic entropy, where non-deterministic outputs from one agent create a feedback loop of errors across the entire system. Senior engineers must identify this threshold early by monitoring the signal-to-orchestration ratio. If your agents are spending more time validating each other's JSON outputs than executing business logic, your architecture is failing. This brings us to a critical realization about the CAP theorem in the age of AI. So if pure swarms are dangerous, what is the architectural alternative that senior engineers are actually moving towards? The industry is currently witnessing a tactical retreat from fragmented micro-agent swarms toward what I call modular monolith agent designs. Much like the evolution of microservices, we realize that extreme decomposition leads to unmanageable complexity. In 2026, the winning strategy is to build a highly capable core controller that utilizes strictly typed deterministic subroutines or tools rather than autonomous chatty agents. This approach minimizes the non-deterministic surface area. Instead of 5 agents passing ambiguous natural language messages, you have one primary agent that calls specific function modules with validated schemas. This agentic monolith preserves the reasoning capability of LLMs while enforcing the reliability of traditional software engineering. It acknowledges that autonomy is a liability in production systems unless it is strictly bounded. We are moving away from letting agents figure it out toward directing agents through clear protocols. This structural shift is only the beginning. The real change lies in how we manage these systems over the next 3 years. Looking ahead to late 2026 and beyond, the primary engineering challenge will shift from agent orchestration to agent governance. We are entering an era where building an agent is trivial, but ensuring it remains compliant, safe, and efficient at scale is the real hurdle. Future frameworks will act less like libraries and more like agent OS or control plans, similar to how Kubernetes manages containers. We will see the rise of real-time hallucination monitors and cost circuit breakers that automatically kill agent processes that fall into incident loops or start generating toxic outputs. The focus will be on predictability over autonomy. As a senior developer, your value won't be in writing prompts, but in designing the governance structures that prevent these autonomous systems from breaking your distributed software. Multi-agent systems are a powerful tool, but as we've seen throughout this course, they are still bound by the laws of distributed systems. Now you have the framework to decide if your project is ready for them. This concludes our deep dive into the resilient agent architectures of the future.